Section 9.3, hyperbolas. A hyperbola is a set of all points x, y in a plane. The difference of whose distances from two distinct fixed points is constant. So very similar definition from an ellipse. The difference is the ellipse was the sum of whose distances, and a hyperbola is the difference. So let's take a look at, we got horizontal and vertical. Let's just kind of zoom into the horizontal one so you can see what we have here. The distance from the center to the focus is c units, so that's still the same as it was with an ellipse. The distance from the center to the vertex is a units, same thing as it was in ellipse as well. Now we did have a major and a minor, but these are just called the vertex or the vertices. And then the distance from the center to, it's not a point on the graph, it's going to help us create this imaginary box that will then help us create the asymptotes for the hyperbola. So the asymptotes, you can see, go through the corners of the rectangle or the diagonal of the rectangle. And so that's what we'll use to kind of help us create the asymptotes. And so we'll zoom back out. The vertical is the same thing, just going a different direction now. You can see the main points are up and down, which are vertical. Look at your two equations. Y minus h squared over a squared minus y minus k squared over b squared is equal to 1 for a horizontal. For a vertical, it's y minus k squared over a squared minus x minus h squared over b squared is equal to 1. So what is the difference that you notice there? Well, the positive term, which would be that first one, determines the orientation. So if the x squared is positive, think x-axis, it's horizontal. If the y squared is positive, think y-axis, and it is a vertical. Your a squared and your b squared, well, your a squared will always be with the positive squared term, so it doesn't change. It's always with that positive or that first term as long as it's positive. All right, here are the things that we know about a hyperbola. The transverse axis is a length of 2a. That was called the major axis in ellipse. Now it's called the transverse axis. It's a length of 2a, contains the vertices and the foci, and the center as well. The conjugate axis is perpendicular to the transverse, and it's a length of 2b. Once again, that was the minor axis with an ellipse, just trying to compare the two so you can see the similarities and the differences there. And both of those contain the center. The asymptotes, or two imaginary lines used to graph, passes through the center and the corners of the rectangular box. So it's the diagonal of the rectangular box that I was talking about earlier. HK still represents the center. C is still the distance from the center to the foci. Even though we've changed conics, it still represents the same thing. B is the distance from the center to the edge of the box there. That would be like your minor vertice. And A is the distance from the center to the vertices, or your major vertices is what we called them with an ellipse. Once again, just trying to make those comparisons. Now the asymptotes. Your two equations of asymptotes might look familiar. Y equals k plus or minus b over a times the quantity x minus h, or if it's vertical, it's y equals k plus or minus a over b times x minus h. Now, in reality, once again, we don't want to memorize too much stuff here. This is actually the equation using point slope form of the center, hk, and then those distances a and b. So it's y minus k is equal to usually your slope that we have, x minus h. But our slope is our rise over run, and that's that rectangular box that we're talking about. And so that comes from y minus k is equal to, and once again, it just depends on which direction we'll go, but we'll call it on this one b over a. And then what happens is we get the y by itself by adding k to the other side. So it's k plus or minus b over a times x minus h. So that's where that comes from. That's the point slope form given a point, which would be the center, and then the slope, which is the distance for a and b. And then it changes for vertical because you'll be going the other direction. So we'll take a look at that so you can kind of see that. And then the relationship for a hyperbola is that c squared is equal to a squared plus b squared, where an ellipse was c squared was equal to a squared minus b squared. This represents your longest distance, and if you go back to the graph, you can see that the foci, or the focus, is farther out from the center now, where with an ellipse it was the major vertice. So C now represents your longest distance. Alright, now that we have kind of all the information, let's go ahead and graph our first hyperbola. So it's in the correct form. We need to identify a couple things. The y squared is first, so think y-axis, which means we're going to be looking at a vertical hyperbola. We also have a squared is 9. It's not the largest, it's the first, or it's actually with the positive squared term. B squared would be 16, and then c squared you would add to get 25. Then you can take the square root of all those. Your center, be careful because now your x coordinate is actually second. So your center is at -2, +3. Your vertices are still your A, your foci is still your C. So since it's vertical, your y value will be changing, and with vertices we're adding 3 to your y coordinate and subtracting 3. So if I subtract 3, I'll get 0, and if I add 3, I'll get 6. So the center is at -2, 3. And then since it's vertical, we added 3 and subtracted 3. So here's your vertex by adding and subtracting 3, which match up to the points that we have. The foci is a distance of 5, so we'll do the same thing. We'll subtract 5 from 3, which would give us -2, and add 5 to 3, which would give us 8. But we can also just count 5 units to get the foci. That'd be at -2, 8. And 5 units down, and that'd give us -2, -2. So all those points are on that vertical. Now we need to create that box, which is 4 units away from the center, left and right. And so I'm just going to make a diagonal, or not a diagonal, sorry, a dotted line around the A value, which is the vertice, and then the B value that creates the other side of the box. Then we're going to make a diagonal, once again a dotted line. This is the asymptote that cuts through the center of the hyperbola and through the rectangle diagonal there. Alright, and then that gives us the information that we need to actually graph it, so we can go ahead and graph. We want to make sure the graph gets close to the asymptotes. Goes through the vertex. Same thing on this side. What I don't want to see, just to kind of show you, is this. That's not accurate. When you have those asymptotes in there, we need to make sure the graph is getting close to those lines. So there's your vertical hyperbola. Now what we haven't answered yet is the asymptotes. So y is equal to, now once again, A or B, B over A. Well, let's look at the graph. You're going rise over run. So you're rising 3, running 4. Yes, that is A over B. But once again, not really trying to memorize that, just looking at it. So you're going up 3, so that's plus or minus, because you'll go up 3 and then left 4 or right 4. And then, whoops, made a minor mistake here. We'll go back and fix that. Y is equal to first the K value, which is your Y value of the center. So 3 plus or minus 3/4, and then X minus the -2, which would be plus 2. So those are both equations of the asymptotes. You don't need to break them up. You don't need to write them in slope-intercept form. Just leave them in that simplified form right there. Is perfect. Alright, so that's how to graph. Let's go ahead and look at how to write the equation. This is going to be very similar to what we did with the ellipse. So let's go ahead and get started. We got y squared minus 2y plus blank. Now we do have a negative coefficient with a hyperbola, so we will have to factor out a negative. And when you factor out a negative from another negative, that becomes positive. So when you factor out -4 divided by -4 is positive 1x squared. -16 divided by -4 is positive 4x. and then we're going to subtract that 1 to the other side. Sorry about that. So that is equal to negative 1 plus, and those are the two blanks I'm going to use to complete the square. So half of negative 2 is negative 1. Negative 1 squared is 1. So we add 1 to the other side. Now remember, when we go and do this, we're going to take half of positive 4, which is positive 2, and you square positive 2 and get positive 4. But remember, negative 4 times x squared is negative 4x squared. Negative 4 times positive 4 was the negative 16x. And then now negative 4 times positive 4 is negative 16. So you actually have to add negative 16 to the other side. The negative 1 and 1 cancel, you get negative 16. Now we divide by negative 16. And you'll notice that now our positive squared term, what looked to be y, is now going to flip-flop. Since I have a negative 4 divided by a negative 16, that will now be a positive. So I'm going to put that one first, because usually we want our positive squared term first. So that's x plus 2 squared over 4 minus y minus 1 squared over 16 is equal to 1. So there's the equation of our hyperbola, once again with that positive squared term first, since we did have to divide by a negative. I'm going to stop there. I mean, we could take this and graph it. You know, we know the x comes first, so we know that represents a horizontal hyperbola. The center would be at negative 2, 1, things like that. But right now, just really working on writing that equation. So here's the graph, how to go through that process, and then here's how to write the equation in the correct form. Alright, the last thing we're going to work on is two examples of working backwards. So write the equation of a hyperbola with vertices 3, 5, and 3, negative 7. So once again, I've provided the graph just to give a better visual of this. So knowing the vertices, we can find the center. So the center is the average of the two. So 3 plus 3 divided by 2, don't really need to do that one, but 5 plus negative 7 divided by 2. So that gives us the center of 3, negative 1. So there's the center. Now we need the A and B values. We also know that this is vertical. So you can see that the vertices are vertical from the center. It also gives us the foci, so at 3, 7 and 3, negative 9. Why is that important? Well, we got two things. Center to vertice we know is 6, and it looks like from center to the foci then will be 8. So we know A is equal to 6, B, not B, but C is equal to 8. So our relationship is C squared is equal to A squared plus B squared. So 64 is equal to 36 plus B squared, which means B squared is equal to 28. We don't need to find B, we just need to know what B squared is. So knowing B squared is 28 and A squared is 36, we should be able to write the equation. It is vertical, so what's going to go first? The y. Y minus negative 1, so that's y plus 1 squared. I'll get the denominator in just a second. X minus 3 squared. And then that's equal to 1. Now, the A squared goes with the positive, so that will be 36 here. And then the B squared will be with the X coordinate, which is 28. So we should get y plus 1 quantity squared divided by 36 minus x minus 3 quantity squared divided by 28 is equal to 1. Alright, last example. You can try this one on your own. Just pause the video and then come back and see how you did. So this one, working backwards, write the equation of the hyperbola with vertices 0, 5. So vertices 0, 5, and 4, 5. So now you can see that we are going horizontal with this one. Also the center, you can see, is a little bit shorter distance, so we can see that one pretty easily. So we know that the center is at 4 comma, sorry, not 4 comma, looks like 2 comma 5. That's the midpoint between those 2 points. We also then know the A value is 2. You're 2 units away from the vertex. And then it tells you the asymptotes are y equals 2x plus 1 and y equals negative 2x plus 9. So they're not written in the form that I had given you, but that's okay. We can go ahead and kind of graph these and see where they're at. So 2x plus 1 would be here. I'll change colors here. So, and then the slope is 2, so you can see how it goes through the center. Alright, and then the other one's going to be negative 2 from the center, so that's actually at 9 though, but we'll go down and you can see once again. So you can see that the rectangular box would be right here because it has to go over to the vertex at least. So right there represents that box, which gives you the distance for B to be 4 units. So you can see right here that distance to the outside of the box would be 4 units. So that's enough to figure out what C squared is. So C squared, well actually, do we even need C squared to write the equation? We don't. So I guess I'm trying to find more information than I need. So it looks like we have what we need. It's horizontal. So since it's horizontal, we have x's first. So x minus 2 squared over a squared. It's the goes with the positive term. Minus y minus 5 squared over b squared, which would be 16, is equal to 1. And so there's our equation for the hyperbola. And then lastly, once again, write your summary for hyperbolas.